Hello, this is the last part of experiment number 2. This is about second law of motion. The difference between the first law of motion and the second law of motion is simply the sum of the forces, okay, or the net force. In the first law of motion, or the law of inertia, the summation of force is equal to 0. On the second law of motion, which is the law of acceleration, the sum of forces is not 0. That is equal to mass multiplied by acceleration. In this experiment, the target is to get the value of acceleration in terms of two ways. Okay, so the first way is use the formula for motion, which is acceleration is equal to 2x over t squared. So in that case, we need to get the distance and also the time. Okay, the time needed to travel that specific distance. And then the second one, which is the theoretical value, we need to get all the forces acting on the object and then equate that to mass multiplied by acceleration. But simply in the manual written there is the formula or the theoretical value of the acceleration of the dynamics part. So if you're going to look at the manual, the formula is acceleration is equal to mass of the hanging mass. Okay, so that hanging mass all over the total mass, but the hanging mass should be multiplied by acceleration due to gravity. So meaning the formula for acceleration is simply the hanging mass multiplied by the acceleration due to gravity divided by the total mass, which is the mass of the part plus the hanging mass. So that's the formula. Okay, so I will be performing here this experiment in which I will be getting the time needed to travel the distance, and then I need to set also the distance. Okay, so if you're going to do this experiment, it's up to you if you want to use or to set the distance at 30, 40, 50, 70 centimeters. It's up to you. Okay, so this is according to your choice. Okay, in this experiment, okay, so we have here the table. Okay, so you look at the table. So we'll be needing two hanging masses. Okay, the first hanging mass is 20 grams. Okay, if you're going to look at the setup, so that's the hanging mass. Okay, so that's the mass hanging. So in that case, that is equivalent to 20 grams. Okay, that one is 20 grams. So that's the first setup or the first trial. On the second trial, we'll be using this other mass, which is the 50 grams. And then here, we already computed or measured the mass of the dynamics cart. So we measured that in our experiment number 1. Okay, or I'm sorry, that is part 1. So the part 1 of experiment number 2. So according to our measurement, the value is 517.62. So we don't need to measure that again because the dynamics cart has the same value. Okay, so this is the value. So the mass total here, so this is the mass total. This is simply the mass of, or the sum of the hanging mass and the mass of the dynamics cart. So we need just to get the sum of the two. Okay, that's the mass total. Trial 1, trial 2, and trial 3, so that's the time needed for the carts to travel at this distance. Okay, for this one, so I'll be setting the distance at 60. Okay, so if that is 60, okay, this is 10. So this is the final point, so that's 10. So meaning this will be 10, 20, 30, 40, 50, and 60. Okay, here's the 60. So I'll be placing the, okay, here's the 60. Okay, 10, 20, 30, 40, 50, 60. So the distance here is 60 centimeters. Okay, then what I will do is I will release the system or the dynamics cart, and then I'll be measuring the time. Okay, so I will start. Okay, 1, 2, 3, start. Stop. Okay, the time here is 1.69. Okay, hopefully I'm getting the right answer. Okay, this is 1.69. So I'll be placing here the 1.69 on the table. So the first measured time is 1.69. Again, I'm the only one who's performing the experiment, so hopefully I'm that accurate with the measure. Okay, so that's the first data. Okay, in the second trial, again, I'll be placing here, again, 60. Again, am I correct? This is 20, 30, 40, 50, 60. That will be at 70. Okay, as much as possible, should be not moving, should be at rest. Okay, that should be okay, 1, 2, 3, start. Stop. Okay. Wow, this is also 1.69. Okay, that's also 1.69. Again, hopefully this is the correct value. Okay, third trial. Okay, this is 0.00. Okay, now I am on the third trial. Okay, on the first trial, second trial, I got 1.69. Okay, for the third trial, okay, 1, 2, 3, start. Sorry, again. Okay, 1, 2, 3, start. Stop. Okay, so the reading here is 1.59. Okay, so the time here is 1.59. So I'm not convinced. I want to try another one because I'm not sure if I set up this one with the string on the pulley. Okay, let's try one more. Okay, 1, 2, 3, start. Stop. Okay, so I'll be using the second or the last data, 1.63. 1.63. Okay, now I'll be, so this one is 60 centimeters. I'll be computing for the other data maybe later. So now I'll be computing or getting first the data. I'll be replacing the 20 grams by 50 grams. Okay, now this is 50 grams. So what can you say about the acceleration? Okay, so what is the relation between acceleration and the hanging mass? If we're going to increase, does it mean that if we're going to increase the hanging mass, there will be a greater acceleration? But based on the formula, so the net force is equal to mass multiplied by acceleration. So from the formula, the total force is directly proportional to the mass and also directly proportional to the acceleration. And then, but if we're going to get the value of acceleration based on that formula, so acceleration is the net force divided by mass. So meaning acceleration is inversely proportional to the mass of the object. Okay, but in this case we are not simply talking about single mass, but we are also talking about the mass of the truck, or the mass of the part and the hanging mass. Okay, the same procedure. Now this is 50 grams. Distance is 60. 1, 2, 3, start. Okay, this is 1.10. I'll be placing here the 1.10. Okay, the second trial. Okay, 1, 2, 3, start. Okay, this one is 1.12. Again, hopefully I'm getting the right answer or the data that ideal. Okay, last trial. 1, 2, 3, start. Okay, I'm not satisfied. This is 1.34. I want to repeat this last trial. Because the first one is 1.10, then 1.12, now this is 1.34, although the difference is simply 0.20 seconds, but 0.20 has effect on the data. Okay, 1, 2, 3, start. Okay, this is 1.06. Okay, so I will try the 1.06. But again, I'm not sure if this is the right data. Okay, so the mass total is simply the sum of the two. So this is 517.62, so plus 20. So this is 537.62. And then this one is 50 plus 517, so that's 567.62. And then we need to compute for the average. So the average time is 1.69 So 1.69 plus 1.69 plus 1.63. Okay, divide by 3. So 1.67. So then for the second trial, for the mass with the mass 50 grams, 1.10 plus 1.12 plus 1.06. Okay, so this is 3.18 divided by 3. Okay, so we have 1.06. So the average here is 1.06. Now let's compute for the experimental value. Okay, again, the experimental value, the formula for acceleration is 2x over t squared. Okay, so twice the distance divided by the square of time. So we'll be using the average time. So for the trial 1, or 20 grams, so 2 times, so that's 2 times 60. So 120 all over 1.67 square. So this is 43.03 centimeter per second squared. Now for the second data, okay, we have 50 grams, so that is 120. Again, 2 times 60, that's 120, divide by the value of the time, 1.06. Okay, so this is equal to 113.21. This that big. Okay, I'm not satisfied. 120 over 1.06 square. No, sorry. Again, 120 over 1.06 square. No, I have here a different answer. This is now 106.78. No, sorry, for the last time. Okay, 2 times 60, that's 120, divide by t square. So time is 1.06, 1.06 square. Okay, 106.799, 106.80. So this is 106.80. So 106.80. Now let's compute for the theoretical value. So the formula for theoretical value is simply the hanging mass. Okay, this is the hanging mass multiplied by g over hanging mass plus the mass of the cart. This is the formula. So we have 20 times, so 20 grams times 980 centimeter per second squared over the sum of the two, so this is 537.62. This is grams. So that's equal to 20 times 980, okay, over 532.62. Okay, so this is 36.79 or 36.80. I guess I have a high percent error. Okay, 36.80. Okay, and then for the second one, we have here 50 grams. So 50 times 980 divide by the sum of the two, 567.62. So this one is 86.33. That's too far from 106.80. 86.33. Okay, again. Did I miss something? Okay, so M is 50 times G, 980. Okay, divide by the sum of the two, 567.62 grams. Okay, so the answer is 86.33. Now I'll be computing for the percent error. Okay, again, 43.03 minus 36.80. Okay, divide by the theoretical value, 36.80. Okay, so the percent error is too high, this 16%. Okay, the percent error here is 16.93, that's too high. Okay, so that's how to compute for the percent error. Then obviously, this is 106.80, then the other one 86.33. So the percent error here is really a very big percent error. So meaning I'm not performing the experiment well, because the reason is, well, I'm the one, I'm only the one who is performing the experiment. So maybe that is an excuse. Okay, but technically and ideally, it should be less than 10%. Okay, guide questions, you need to answer 1, 2, 3, and then after that, so we're done with the experiment. Okay guys, thank you so much.